Hey guys, welcome. In the last episode, we upgraded our controller and made it a fully kinematic raycast-based controller. And this means that we no longer have to fight with the physics engine, and now we have full control over everything. And we're going to make really good use of that right now by adding the ability to travel on slopes as well as curved ground from sprite shapes. It is really smooth and it feels really good. However, this is going to require quite a few changes because adding slopes makes us have to think about just about every ability that we've made a little bit differently. How do we handle wall slides now that we have the potential of having sloped ground that's too steep to walk on, but it's not a full 90-degree wall either? How do we handle our dash if we dash with no move input while standing on a slope? What do we do when we step on a slope that's too steep to walk on, but it's not steep enough to be considered a wall? What kind of changes do we need to make to ensure that our head bump slide mechanic takes all angles into account now? Do we let our player jump when they're on a slope that's too steep to walk on? And what kind of changes do we need to make to our buffer and coyote timers now that we're adding slopes into the mix as well? These are all things that are going to require changes, and we're going to do it all right now. And it is worth the work, I promise you. If you want to test out how the player feels before committing to following the series, I've uploaded a little test level on itch.io, so grab a controller and test it out if you like. And if you do like it, you can get the same controls for your platformer by following this series. Ready? Let's go. Now, before we get into anything new, I want to fix a couple of things. And the first is our head bump slide mechanic. Under just the right set of circumstances right now, you can end up in this weird loop where he just goes left and right over and over and over and it never ends. And we're going to need to change two things to fix this. And the first is we're going to add this, which is going to let us track whether we've actually started a head bump slide during this jump or not. And we'll add that in here in our HandleHeadBumpSlide so that we can't start head bump sliding if this is true. And actually we'll also set that to true here as well. Now, obviously we need to set it to false somewhere, and it's going to be any ability that can get us airborne or if we just landed. So we're going to put it in our landCheck, in our initiate jump, initiate wall jump, and also in initiate dash if our dash direction .y is greater than 0. So we are at least moving up somewhat. Okay, so that's fix number 1 for the head bump slide. Fix number 2 needs to happen over in movement controller. Right now, our vertical rays are affected by our X velocity, and that is good for our feet. We need that sometimes, but we don't want it on our head rays while we are head sliding. Otherwise, our head rays are probing for ceiling further than the player actually is, and it doesn't play nicely with the rest of our head slide logic. So to fix that, we need to separate our head rays from our feet rays. And that is going to require almost a complete rewrite of the resolve vertical movement method, but that is fine because our slope logic is going to require basically an entire rewrite as well. So we're just going to do both at the same time. And in order to do that, we need to add our new variables to let us handle slopes. So in player movement stats, under head bump slide, we'll add this. And we'll add a new slopes header with all of these. Under reset jump options, add this. We're going to add these under the wall slide. And these 3 new ones under the debug section. Okay, so that's everything in that script. Now we're going to go back to our movement controller. Now we need to keep tabs on quite a lot of different things for slopes. So here is everything that we're going to need. And before we do anything else, let's not forget, we're going to set our face direction to 1 in awake. We'll go through what that is in a little bit. And in reset collision states, we need to make sure that we're resetting all of our new variables as well. Okay, now inside our resolve vertical movement, first, we're only going to run our head rays if we're not moving down. We're going to set our ray length and then run a for loop to iterate through every ray. And I did do a lot of testing with this, and it is very important that we check for the head race first before we do the feet. So we can just move our debug visualizations for the head race to be inside that new for loop. And this here is going to stay almost exactly the same, so we can cut it and we'll paste it in here as well. And now I'm going to get rid of just about everything else because it needs to be rewritten to handle our slopes properly anyways. Now for our ceiling check, we're just going to always start our ray origin at our top left. And right here, this is the fix for the head bump slide. We're going to set our horizontal projection to be our x velocity, but if we are head bump sliding, we're going to make that 0. And now we'll plug in that horizontal projection instead of our velocity.x directly. So now it's only going to look ahead based on our velocity at the appropriate time. And we need to go back to our player movement to make is head bump sliding public. Okay, so we'll call our array. And if it hit, we're going to need our ceiling angle because our jump and our head bump slide are going to need to know about that angle. And if the hit distance is 0, then we're flush against the ceiling, so we can stop our y velocity immediately. But with raycasts, if your hit.distance is 0, then the normals that your raycast returns are often going to be unreliable. So what we're going to do is we're going to cast another ray, but we'll position it down slightly to be sure that it actually does hit the ceiling. And if that safety ray hits something, then we're going to grab our angle and ceiling normals from that. If it did not hit, then we'll just use a fallback of 0 degrees and vector2.down for the normals. Now, if our hit distance was not 0, then we'll change our y velocity to our hit distance minus our collision padding amount. We're going to shorten the ray length for all our future ceiling rays and grab our angle and normals. Now we're still working inside the if hit block, so is colliding above is definitely true. And we can also set our corners here. We started at the top left, so if it's the first ray, then our left corner hit, and if it was the last, then our right corner hit. And since we're casting multiple head rays, it is possible that they each get different angles depending on the shape of the roof. So we'll make the highest angle the current angle that we store. We're going to move this into the if hit block. And for this check, the only change that it needs is if the current ceiling angle is less than or equal to our max slope angle for head bump. Okay, so if we want to actually test out our head bump slide to make sure that we fixed it, we sort of have to finish our vertical raise check because right now we're just going to fall through the floor. So if we're moving down, then we'll make our ray length our y velocity plus our collision padding. Otherwise, if we're not moving down, we'll make it as long as our collision padding times 2. For the ground, we're going to be storing our smallest hit distance. Now we'll iterate through each ray. We'll always start at the bottom left. Ray origin moves it over by our vertical ray space and takes velocity into account. And then we cast our ray. And if we get a hit, and if our current hit distance is less than our smallest distance, then we're going to store that one. And our debug visualization should be fine. But outside of the for loop now, we want to say if we found ground, then is colliding below is true. And if our velocity was less than or equal to 0, then make our velocity.y equal our ground hit.distance minus collision padding times minus 1. Now we'll grab our slope angle. And to avoid certain edge cases, we need to check if the ground that our vertical ray is finding is technically supposed to be a wall, because at certain angles that could be true. And if it's not, and our slope angle is greater than 0, then store that slope angle and slope normal. And if we did not find ground, and we're on a slidable slope, then we'll set is sliding to true. Okay, so we do have more to do before we have full slope support, but now you can see that our HandleHeadBumpSlide has been fixed. Now, before we go back to slopes, I do have a few more little fixes and improvements. In player movement, we're going to go back to our handle horizontal movement. First off, our turn check should be here. Otherwise, it is technically possible for our player to turn even though we aren't moving, which we definitely don't want. Also, we have this exact same check in here twice, and that's just kind of poor form, and it could be condensed to be both faster and more readable. So we're going to move our acceleration stuff up here. Move this line inside. And get rid of this. And our deceleration to 0 will just go in this else statement. We can get rid of this here and just declare it right here. So the way that we're using our lerp here, we're feeding the result from the last frame back into the lerp again. It makes our acceleration and deceleration exponential, which means with this calculation here, we're moving towards target velocity X, and we'll get infinitely closer and closer to our target, but we will never actually get there. And that can make velocity checks very unreliable and very confusing. So we're going to fix that. And also, just to be extra careful, we're going to clamp our acceleration times time.fixedDelta to be between 0 and 1, because anything outside of that range could really screw up this calculation. But now if we're within 0.01 away from our target velocity, then we're close enough, and we're just going to snap it to our target velocity so that we actually do properly reach our target. And we'll do the same if we're pressing nothing. If we're close enough, we will just snap it to 0. Okay, this next change is really easy, but it is one of the most important ones that we're going to make for this controller, and it was the source of a lot of annoying little bugs that I had a lot of trouble figuring out while building this controller. So our turn check, it needs to change. Remember, our goal with this controller is to make it deterministic. So no matter the frame rate or hardware, it doesn't matter. Our player is always going to produce the same output for our button presses. And right now we're turning by flipping the Y rotation of our parent game object. And our transform and the physics update at different intervals. So if we change anything with the transform, it can give us 1 or 2 frame glitches or little issues that are basically impossible to track down because there's a timing issue. So instead of flipping the parent object, what we're going to do is move all of our visual components to a child object, and we will flip that. Our rigid body is on the parent, so this is perfectly fine. They won't affect each other. So we're going to add a child. You can call it whatever you want. But make sure that all of your character art gets put under here. And if you have an animator, it should be moved to this game object as well. I don't have one for this character, but if you do, it should be here, not on the parent. And there we go. Another thing that's just kind of been bugging me is this little bit of logic in the landCheck method. The logic is good, but I would like to move it into its own method to keep things cleaner. And before we can do that, we need to add this little helper method that we can call to see if we are standing on a slidable slope. Now, we do not want to do this if we're sliding and only if we're grounded, and also if we're not on a slidable slope. If all of that is true and our velocity is less than or equal to 0, then we'll reset it to our rest downward force of -2. And we'll call that in fixed update right after our dash check. Okay, with all of that done, let's finish implementing the rest of our slope logic. So back in our movement controller, let's improve our resolve horizontal movement. If our X velocity is 0, then we are going to have to rely on our face direction instead of our velocity, because if what we pass into math f.sign equals 0, that formula actually returns 1, which we do not want, so this is going to be our fallback. Also, if our X velocity is less than our collision padding, then our rays should be at least twice as long as our collision padding so that they have some length to them. First, we'll return our slope angle and see if what we're running into is a slidable slope. If it is, then we're on a slidable slope. And these two lines are good here. We set our X velocity to hit.distance minus collision padding multiplied by our direction. And our ray length for the next iteration will be our hit distance. If we're already climbing a slope, then we have to resync the Y velocity to the slope geometry, or we can get weird jitter or a brief little hop off the ground when we hit a steep section. Then after we update our collision bools, we continue. Meaning, with this current ray, don't perform any more logic. We're going to skip to the next ray in the for loop. We're going to do the same thing if we're sliding. Now next, if this is the first ray, meaning the one closest to our feet, and the angle that we picked up is less than our max slope angle, then we're climbing a slope. And we'll create this method in just a minute. But again, here we continue. We also continue if we're climbing a slope regardless of which ray it is. We just only want to call this here once. So this block will be for the rest of the rays. Now, if any rays made it past all of that, then we again set our X velocity based on our hit distance, collision padding distance away, and reset the ray length. And now if we made it past all of those checks, what we're hitting could be a wall. So we're going to record our wall angle. And we need to do this again, just in case we weren't on a slidable slope before. And finally, again, update our collision bools. Okay, and we actually need to do one more thing at the end of our resolve vertical movement. Our climb slope is called from our horizontal, which runs first. However, we have to add this check at the end to recheck horizontally from our new vertical offset to see whether the slope in front of us has changed at all. If we don't do this, then sometimes we can end up just slightly inside of the ground when climbing up, which obviously we don't want. And also we'll add our debug visualizations here so we can see the slope normals when we're climbing. All right, next we need to actually set our face direction in move right before we resolve any of our movement. And before that, we also want to call our descend slope method, which again, we're also going to create in just a second. But we also need to change our is dashing inside player movement to be public as well. All right, before we get back to our slope logic, I want to thank this video's sponsor, Coursera. We are deep in the weeds right now with this controller. We've required custom raycasting, vector math, and trigonometry, handling dozens of edge cases just to make our character walk up a hill. If you are following along with a fairly complex tutorial like this, then you're clearly pretty serious about mastering your craft and building a professional skill set. And that is exactly why I'm so excited to be partnered with Coursera. Coursera is an online learning platform offering thousands of courses, specializations, and even professional certificates from world-class universities and companies like Google, Microsoft, and top computer science programs. Throughout this series on YouTube, we've spent just a couple of hours on one aspect of physics. On Coursera, you can take an entire in-depth specialization on Unity development. You can master the data structures and algorithms that power controllers like this one, or even dive into game design principles or C# programming for Unity game dev specialization. It is the perfect way to build those job-ready foundational skills that take you from following a tutorial to designing an entire system by yourself. So check out the link in the description if you're ready to get started and get 40% off for 3 months of Coursera Plus. And again, huge thanks to Coursera for supporting the channel. All right, let's finish this controller. Now down here, here's our climb slope. We're gonna get our move distance. We're going to compute the required vertical distance that we need to follow the slope. And then we only want to apply the climb slope velocity if our y velocity is less than the climb velocity. Then we'll actually set our velocity. And now we'll adjust the horizontal distance to match the slope's angle. And set our bools and our slope angle and normal. Okay, so that's our climb slope logic. Now we need our descend slope logic, which is completely separate from our resolve movement methods, and it runs before them. And before we do the regular descend slope logic, we're going to cast 2 rays, one from the left and one from the right, and we'll send them down by our y velocity. And then we do this. This is a bitwise XOR operator, which basically means if we hit left or right, but not both. If that is true, then we'll call our slide down max slope function. Now, if we are not sliding, then we'll get our ray origin based on our face direction. Now, it's worth pointing out because this is the opposite of how we usually do it. So we're trying to cast a ray from our rear foot, basically, instead of the front foot. So this is backwards compared to what it normally is. And we can use this formula to determine how long our ray needs to be to hit our max slope angle based on our X velocity. Then we cast our ray. And if it hits, we get the slope angle and call our apply slope stick method. And here is the debug visualization code if you want to see your descend slope ray. Okay, first, let's make our apply slope stick method. This makes sure that our player actually sticks to the slope, and it's really important to get this one right. Otherwise, everything's going to feel jittery, or your player's just going to bounce when going down slopes, and it's really annoying, and it just doesn't look good. So we're going to check if the vertical distance between the collider and the ground is small enough that we should consider ourselves on the slope. If that is the case, then we should snap onto the slope and follow it. So to do that, we add our move distance, which is how far we're trying to move, and our descend move amount y, which is how far down we should move vertically to stay on the slope during that horizontal movement. And now we recalculate the move vector to actually follow that slope we just calculated. And then we set our bools and our slope normals and angle. Now, finally, let's make our slide down max slope method. This is what happens when we are on a slope that is past our max slope angle, but it's not steep enough to be considered a wall either. So if our ray hit, we're going to grab the slope angle. Also get the wall direction based on whether the normals point to the left or the right. And we want to know if we're facing a wall, so we need to compare the wall direction and the player's facing direction. We also need to know if this is a normal slidable slope or if it's a wall slope. And if it's a normal slidable slope or it's a wall slope, but we are not facing that wall, then we let the slide happen because we only allow wall slides when we are facing a wall, not facing away from the wall. We're also going to clamp our tan angle to avoid any potential divisions by 0, which would give us an error. And then we calculate what our X needs to be to follow this slope smoothly. We're just going to handle Y completely separately in our player movement script. And again, set our bools and our slope angle and our slope normals. Okay, so that is the bulk of the work done. Our raycasts are going to handle and calculate our velocity properly on slopes and regular ground. Now we just have to go through our player movement controller to add in all the little nuances to make this all play nice with our existing movesets. So first I mentioned we would handle the Y velocity in our player movement for the slide method, so we're just going to go ahead and do that right now. These are the only two variables that we're going to need for all additional functionality for slopes. I always like just getting variables out of the way first. So our handle slide method is very, very simple. If we're sliding, first of all, if we jump, cancel out, same if we wall jump. That's our escape from the slide apart from hitting the ground. But if we make it past that, then we're just going to increment our Y velocity by gravity times our time step, just like normal gravity. And in fixed update, we can call this right after fall down here. Next, we added a slide speed to our slide, but currently our clamp velocity would stop it from actually getting to that speed. So let's adjust this so that if we're sliding, we clamp the Y to minus slide speed. Dashing can be the same as it was. I'm just going to swap these. And other than that, we'll clamp it to our regular fall speed. Okay, next, our head bump slide in this script has no idea about angles, so we need to make it just a little bit smarter. First off, delete this. We don't need it. Down in our HandleHeadBumpSlide, we can just check our controller's head bump slide direction. Now up here, first off, we can return out if we're wall sliding or sliding. But also after that, we want to make sure that our current ceiling angle is less than or equal to our max slope angle for head bump. If that is true, then we'll allow ourselves to head bump slide. Okay, next, our landCheck needs to be aware of slopes that are potentially a wall. Because if that's the case, we don't want to play a land animation. So if that's the case, we just return out. And also at the bottom, we may or we may not want to reset our air jumps depending on our options and whether or not this is a max slope. So we only allow that if we set reset air jumps on max slope land to true, or we set that to false, but we're not on a max slope. Next, we need to take our options into account for our jumps as well. So for a regular jump at the end, we'll add, and we can jump on max slopes, or the slope isn't a max slope angle. For the double jump, we just add in an or here to check if we're sliding. This means that if we're sliding, we'll use an air jump to get off the slope rather than a regular jump, which to me feels fair. Now, when we were working with just 90-degree angles, it felt right to just stop our Y velocity if we bumped our head on a ceiling, but now it just doesn't seem right to me anymore. So what we're going to do is calculate our velocity based on the ceiling normals so that we'll kind of just slide along the slope in a way that feels and looks right. So in our jump function, right after this if statement, we'll say else if we have our jump follow slopes when head touching set to true, and we actually have a ceiling angle. If that is true, then we grab our normals and say our velocity is equal to our velocity minus the dot product of our velocity and the ceiling normal times the ceiling normal. And that's it for that. And we need to add the same thing to our wall jump here. And very similar logic in our dash function as well. The difference being here that we have a dash follow slopes when head is touching bool. All right, and since we're at the dash, let's fix the rest of it. Right at the end of our initiate dash function, we're going to check if we're performing a dash slope. That'll be true if we're grounded and we have a positive slope angle. We're dashing horizontally. We're not jumping. And the sign of our dash direction is different than the sign of the slope angle. If all of that is true, we're performing a slope dash and we should set the slope dash angle. And now that we have that, in our actual dash function near the bottom, we'll check if we want to match our dash direction with the slope direction and if we're performing a slope dash. If so, here's how we can calculate what the direction of our dash needs to be to follow the slope smoothly. And all of this logic here can be wrapped in an else statement. And if you want to visualize it to prove to yourself that it's working, you can add this little visualization logic here. And you can see when we dash on a slope that the line is parallel to the slope. Okay, now that we have slopes, we have walls that are not perfect 90-degree angles now. So our wall slide check needs to be a little bit smarter as well. So we want to know if we're touching a sidewall. And we want to know if that wall is within the appropriate wall slide threshold. And now we'll change this just slightly. I'll move not dashing to the front. And we want to make sure that we're touching a sidewall and is it at the appropriate angle and we're not grounded. And now we can simplify this check down here and just say else if we're wall sliding and we're not touching a sidewall. We also need to make our should apply post wall jump buffer smarter. So again, we want to make sure that we have a valid wall angle. And if we're touching a wall and it's a valid angle, or we're already wall sliding, then we return true. Finally, we need to make our timers a little bit smarter as well. We're going to make a proper handle coyote timer and handle dash on ground timer method. So now you can delete this and this and replace it with those methods. For the coyote timer, we only want to set our coyote timer if we're grounded, but we're not sliding and we're not on a slidable slope. Otherwise, we decrement the timer. And basically the same thing for the dash on ground timer, only decrement the timer if we're grounded, we're not sliding, and we're not on a slidable slope. If we don't do this, then your players can exploit some of those timers to do things like jump on a slope regardless of your settings. So this will fix that. And one day I will get through one of these recordings without making a typo or a mistake, but today was not that day. So right now, if you play, you're just going to float up into the air. And that's because we need to wrap this in our jump checks in brackets. Another fix over in movement controller down in the slide down max slope. This should be slope angle with a small s here. And in landCheck, we also want to move this block out of this if statement so that it's running basically all of the time, not just when we first land. Our reported slope angles are from the last frame since we call our move function at the end of every fixed update. So because of that, we have a 1 frame desync. So we need to check this constantly as a result. And a little debug correction in movement controller in our reserve vertical movement, we are not taking our X velocity into account with our debug raise, but we should be. So in the ceiling check, go ahead and add the horizontal projection. And in the ground check, you can just add the velocity.x. Okay, back in player movement, go to the dash function. Right now, if we dash on a slope, we get this weird little hop at the end. We can fix that by going down here and setting our velocity.y to 0 if we are grounded. And finally, in reset dash values, we should be setting is performing slope dash to false here as well. And that is finally it. This was a lot. I know this was a monster tutorial. Adding slope handling is not an easy thing. So there was a lot to cover, but your controller will now handle slopes really well, and your player is going to stick to the ground no matter what the slope is, which is really nice. And by default, right now, they already handle sprite shapes really nicely as well. My only word of caution with that is to use polygon collider 2Ds, not edge colliders on sprite shapes. You generally want to use colliders that have some sort of volume to them when you're using a raycast controller, or you could wind up clipping through the ground or a wall under just the right set of circumstances. I'm not exactly sure when the next episode in this series is going to come out, but in the next one, we're going to refine this a little bit further and add even more nuance so that we don't necessarily stick to every slope, because we're going to add some speed and angle thresholds so that we can actually run off and make everything feel a little bit more natural based on the angle and the speed of our player. And if you want to rotate your character based on the slope normals, there is a trick to that, even handling like really sharp corners as well, like this. So we'll handle that as well. But thank you so much for watching. If you want access to this controller in a state machine with animations and all of that, you can grab that over on my Patreon. So thank you so much if you choose to support me that way. And I will see you guys soon.